Hello there. This lecture is all about probability. And you've seen probability before when we looked at frequency distribution tables, but I'm also going to show you how to figure out the probability of certain scores when you do not have access to raw data. So the first part of this lecture will somewhat be a review of the frequency distribution table lecture, and then we'll move into using the unit normal table when you have a normal distribution and you know what the z-scores are to then figure out the probabilities associated with scores. So again, I'm just going to cover basic probability in the frequency distribution tables, so the P column, essentially, in a frequency distribution table. Then what is a random sample? So I'm going to get into what is the criteria to call something a truly random sample and why random samples are important in inferential statistics. Then I will show you how, again, review of the empirical rule and probability in the normal distribution. And then I'll use the unit normal table to prove the empirical rule and the normal distribution. And then the follow-up lecture for this lecture will be the example problems, where I'll go through several examples of using the unit normal table and z-scores to figure out probabilities and to figure out scores associated with probabilities. So this formula should look somewhat familiar to you. So this is just the probability formula. Remember, probability and proportion can be used synonymously with each other. It just depends on, the context of what you're asking. So P equals F divided by N. So the frequency of a specific score, or the number of a specific outcome, divided by N, the total sample or population size that you're looking at. All of the possible outcomes. All of the scores. How many scores are there in total? Another way to think about it. And then to get percent chance, you just take the p-value and multiply it by 100. Alternatively, if you have something like a percent chance, like something is a 50% chance, divide 50 by 100 and you have a probability of 0.50. So this table includes the full frequency distribution table. So we have all of our scores here, all of our x values, and in this particular example, we're looking at how many pizza slices have you consumed in the past month. So as even more review, think about what is the scale of measurement for this variable. Okay, so it's a numeric value, right? How many pizza slices? And we can go ahead and call this ratio instead of interval because there's a true 0 point. 0 means complete lack of pizzas. And as another review, is this a discrete or a continuous variable? Think about it. So it's continuous, right? Because you could take half a bite out of a slice of pizza and have a fraction of a piece of pizza. It's not limited to whole numbers. Okay, even though it looks like whole numbers here. Then this column, frequency column, right? So how many college students said that they ate each one of these numbers for pizza slices in the past month? So 2 said they ate 6 pizza slices in the past month. 2 said they ate 5. 2 said they ate 4. 7 ate 3. 20 students said they had 2 slices of pizza in the past month. 12 said 1, and 1 said 0. I think I would I would be an outlier here. I eat pizza all the time. I don't even think I'd fit into this table. So when you think about, if we go back to this formula, the number of all possible outcomes, this gets at the sum of the frequencies if you're looking at a frequency distribution table, or the sample size, or in this case, I'm calling this a population. So the population size. So you just add these numbers together. That gives you the denominator of your probability formula here. So how many possible outcomes are there? Well, there's 46 students. So if you're randomly selecting a person, you're randomly selecting from this pool of 46 people. So then to find the probability or proportion, remember you can state it either way. You just take the frequency for that particular score. So the number of that specific outcome. So 2 students with 6 pizza slices. That would be the outcome in this case. 2 divided by 46, 0.043. So you just take the frequency for each value, divide it by the total frequency of all values, and you get your probabilities or proportions. So after you do that, you can convert this into a percent chance. People are typically more comfortable expressing things in terms of percent chance instead of the probability or proportion. So you just take what you found here, multiply by 100, and you get a percent chance. And then remember, cumulative percent or percentile tells you the percentage of scores, or sorry, the percentage of the sample that had a score that's equal to or less than that particular score. Or in this case, the percentage of the population that had a score equal to or less than a particular score. So that's why you start with the bottom. So the cumulative percentage or the percentile for 0 is 2.2. 2.2% of this population consumed 0 or fewer pizza slices. And because this is ratio and 0 is the smallest value in our data set, there's nobody who consumed less pizza slices than 0, so you just steal that percentage and just put it here. Well, then moving up. So how many students consumed 1 or fewer pizza slices in the past month? Well, if 0 was 2.2% and then 1, 26.1%, you add those together and you get 28.3. And then moving up, you just take the cumulative percent for the value just below 2, so the cumulative percent for 1, add it to the percent for 2, and you end up with the cumulative percent for 2. So 71.8% of this population consumed 2 or fewer slices of pizza. And then you just kind of add all the way up until you end up with, within rounding error, 100% of this population consumes 6 or fewer pizza slices in the past month. So I review this because the interpretation of the unit normal table is often based on percentiles. So it's important for you to understand the concept of percentiles. The percentile just tells you the percentage of scores less than or equal to a specific score. So you can answer several questions with this table that you wouldn't necessarily be able to answer if you just had raw data on a screen. So what is the probability of randomly selecting a person who ate 4 pizza slices in the past month? So out of this population, the probability would be 0.043. So you just find 4, go to that probability. You could also say that the proportion of students who ate 4 pizza slices in the past month is 0.043. Or you could say 4.3% of students in this population ate 4 slices of pizza in the past month. Or you could say you have a 4.3% chance of randomly selecting a person from this population who had 4 pizza slices. All those things using that same number. Just depends on the way that you want to state it. And then before I leave this slide, I just want to mention that when you add up all of your proportions or probabilities, you should get something close to 1. And when you add up all your percentages, you should get something close to 100%. Because 100% of this population ate between 0 and 6 pizza slices. So here's another question that you can answer using the frequency distribution table and the raw data. What's the probability of randomly selecting a person who consumed 3 or fewer pizzas? So this is asking you for a percentile, right? 3 or fewer. So you go to 3, go over to the percentile, and you see that it's 87. Well, you could also add up, so 3 or fewer, you could add 0.152 to 0.435 to 0.261 to 0.022. You'd get the same answer. Or you could say 1 plus 12 plus 20 plus 7 divided by 46, and you get the same answer. Here in a little bit, I'll show you how to get these kinds of answers when you have no access to the raw data. All you know is the mean, the standard deviation, and the fact that you have a normal distribution. Here's another example of a question that you can answer. So, what is the probability of randomly selecting a person who consumed more than 3 pizza slices? It shouldn't be pizzas, it should be pizza slices. So if we look at this, more than 3, so 2 plus 2 plus 2, you could add those together, get 6 divided by 46, get 0.129. You could add these 3 together and get 0.129. But you could not go to, oh, okay, greater than 3, I'm going to go look at the percentile. That's not going to work. This percentile tells you the percentage that had 3 or fewer, not more than 3. So although you can't go to the percentile for 3 and get your answer, if you think about it, this tells you the percentage of people in the population who had 3 or fewer. Well, if you're working with 100% of the population and 87% had 3 or fewer, well, 100 minus 87, 13% had more than 3. That represents these people here. And you can see this is within rounding error if we multiplied this by 100 of 13%. So just getting you comfortable with interpreting the values in this table. So here's another one. Probability of randomly selecting a person who consumed between 2 and 4 pizza slices. Well, you could go right to the table and you could say, okay, between 2 and 4, 20 plus 7 plus 2 divided by 46, that would give you about 0.630. You could also go here and say, all right, add my probabilities, and that would give you something close to 0.630. Now again, you're going to be seeing questions that kind of look like this in the future, but you're not going to have access to the raw data. You're going to calculate a z-score, and then you're going to use the unit normal table to figure out these probabilities. So I want to tell you guys all of the criteria that have to be met to call something a true random sample. And the importance of a random sample is that each person in the sample had an equal probability of being selected. So that's where probability comes into play with random sampling. So the two criteria for a true random sample would be random and replacement. So random is just that you have access to the entire population and you're just randomly choosing people, not based on any pre-selected criteria. So everybody is in your pool and you're drawing from them randomly. So think about a non-random sample, for instance. So let's say that I was going to do a study where I was trying to use a sample of my students to figure out what time people arrive to class. So I'm trying to figure out, do people arrive early? If so, how early? Do they arrive right on time? If they arrive late, how late do they arrive? And let's say that I decided to select the front row in my class and ask them, what time did you get to class? Well, that's not random, right? It's based on where they're sitting in the room. And that could contaminate your results because maybe the people who sit up front tend to be more into the class and tend to come early, and maybe they came early to make sure they got their front row seat. You know, because the lectures are just so engaging. They have to be right up front. It's like hot seat for everybody. I don't know. There could be several different reasons why sitting up front could have an impact on the time that you arrive to class. So that would not be a very representative sample of my population of students in the class. However, if I just put everybody's name into a hat and randomly picked out 5 names, it's not based on where they sat. It's not based on anything other than random chance. So it's highly unlikely that you're going to have some kind of contaminating factor that results in you having people who are coming early or late. It's just going to be random. Now, luckily, in statistics, we can statistically control for random error. We cannot control for systematic error with our statistical analysis. So we couldn't control for the fact that I selected people from the front row, but we could statistically control for the amount of error we would expect to see, the amount of sampling error, based on the sample size and how spread out their scores are. But we'll get to that when we get to hypothesis testing. So that's randomness, right? You're just randomly picking people out. Replacement gets at the fact that once you make one selection, that person goes back into the pool of to be selected. So hypothetically, the same person could be selected more than one time. So back to my, what time did you come to class example. So let's say that I picked a name out of a hat. So I'm doing some random sampling, picked a name out of a hat, said, okay, what time did you come to class? All right. And then I put it back into the hat. And then I pull another one. So each selection is coming from the same pool. So let's say that I had 30 people in my class. Well, let's see. If you calculate 1 divided by 30, you could see that for any given person, they have a 0.033 probability of being selected. Now you put that person back in, and then the next person also has a 1 out of 30 chance, or a probability of 0.033 chance of being selected. But if you don't put that person back in, so let's say we draw one selection, 1 out of 30 chance. All right, now we draw the next selection. Now it's a 1 out of 29 chance of being selected. The next selection, 1 out of 28 chance. So you can see the probabilities changing with each selection if you aren't doing replacement and you aren't putting that person back into the population to be drawn from. Now, I will admit, true random sampling is the best way to minimize the impact of individual differences contaminating your results and to make sure that you do have a sample that represents your population. But it is an extremely rare thing. it's difficult to have a true random sample. Because even if you start off with access to the entire population and you're doing random sampling, in behavioral sciences, usually ethics comes into question if you force people to participate. So even if you start off with a true random sample, you may end up with a more of a convenient sample because people actually volunteered to participate in the study once they were chosen. If you're doing, archival data in a business, or if you're just looking at attendance or something that you already have access to and you don't have to ask people to participate, then it's much, much easier to have a true random sample. So this little flow chart shows how random sampling impacts inferential statistics, which is where we're going to be heading in, I think, the next lecture. We're going to be talking about inferential statistics. So if you start off with a random sample, and a large random sample, larger samples are always more desirable, right? They're going to be an more accurate representation of the population. So you start off with a large random sample, and then you're pretty confident that that sample represents your population. So if you're measuring a dependent variable, you are assuming that whatever they have for their dependent variable, your sample, they look pretty similar with their dependent variable as the population does. So then you can, if you're doing an experiment, manipulate some conditions. So you can, for instance, let's say that we want to look at a drug study and we're looking at how drugs impact pain. So you could randomly sample everybody who has chronic pain. So they could have back pain, they could have multiple sclerosis, they could have arthritis, all sorts of different types of pain. And then you would think, okay, we've got a nice, big random sample. They probably represent, the variation of different types of pain, different levels of pain in the population. Then you can manipulate some conditions. So let's say that if we're doing the most basic type of study where we are comparing a sample to the population, and let's say that we know the pain level of the population. So we give these people this new experimental drug. So that would be the manipulated condition. We give them this drug, and then we measure their pain after they've been on the drug. And then we see if that sample that originally represented the population on pain still represents the population. And the way that we make that decision, does this sample still represent the population after we've manipulated the independent variable? Or in this example, does this sample still have the same mean level of pain as the population after we gave them this drug? The way you make that decision is you're looking for an extreme z-score. So you measure scores on the dependent variable, you measure pain. Oftentimes when you're using a sample, you'll actually calculate the sample's z-score. But let's say that we look at the z-scores for everybody in our study. So we calculate the z-scores for their level of pain. And if we have an extreme z-score, in this case we're probably hoping for a z-score that's extreme on the low end, right? Less pain. Then that means that that score has a low probability of randomly being selected from the population. Or in other words, it's a low probability that that person still looks the same as they did before they got the drug, or that it's a low probability that you would see this effect if the drug actually wasn't working. So that's getting to, more hypothesis testing that's to come, not today. So if you have a random sample, they represent the population, you manipulate something, then you measure the dependent variable, and they no longer represent the population because they have an extreme z-score, then you can be pretty confident that your independent variable had an effect, and you may be able to actually say that it's a significant effect. And then that results in a better understanding of nature. Even if you find that the pain levels didn't change, for example, they still represent the population who wasn't taking this experimental drug, you still have a better understanding of nature. You know that, physiologically you're not reacting to this type of drug. So that's why random sampling is important, because you have to assume that your sample represents the population if you're going to compare your sample after you manipulate something to the population to see if things have changed. Now, as you get through, later chapters in this class, you'll see that there are more sophisticated designs when you don't have to even rely on the population at all, but we've got to start somewhere, and we're going to start with the basics, comparing a sample to a population. So let's look at random sampling and how to calculate probabilities when you're doing random samples. So let's say that in Psychology 210, there's 11 males and 27 females. So if we go back to that formula, if we're randomly selecting a student from this class, 11 plus 27, the entire class, so there's 38 people in the class, that would represent the denominator of your formula, the number of all possible outcomes, the total number of students in the class. And then if we're looking at the number of a specific outcome, so the numerator, if we are selecting a male, there's 11 males. So the specific outcome is selecting a male, and then the total number of students in the class would be males plus females, 38. So there's 11 males out of 38 students, 11 divided by 38. The probability of randomly selecting a male would be 0.289. All right. Now the probability of selecting a female from this population of psychology students. Well, 27 out of 38 students are female. 27 divided by 38 gives you 0.711. That is the probability of randomly selecting a female. Now, if you wanted to put these into a percent chance, you could say, just scoot the decimal place 2 spaces to the right, multiply by 100. 28.9% chance of randomly selecting a male. Or you could say 28.9% of students in the class were male. 71.1% chance of randomly selecting a female, or 71.1% of students are female. Now you should notice if you add these two guys together, you're going to get 1. If you turned them into percentages and added them together, you would get 100%, because 100% of the students are male or female. So you would have a 100% chance of randomly selecting a male or female from this class. We're assuming there's no hermaphrodites here. All right, anyway. Moving on to a slightly trickier question. So, what is the probability of randomly selecting a male from the population of Psychology 210 students, still working with the same group, if the researcher already selected 2 males and already selected 3 females? Keep in mind, any time, for our purposes, that you see randomly selected or a random sample, assume random with replacement. So you may be inclined to do some tricky math, right? You may say, okay, well, my outcome of interest. So I had 11 males to begin with, but I already selected 2. So 11 minus 2, I'm left with 9 males. Out of the entire class, so I had 38 to begin with, but I already selected 5. So 38 minus 5, all right, 9 out of 33. That's what's left. Don't see this big X? That's there for a reason. Remember, I said that with a truly random sample, the probability does not change across selections. So you would not want to consider, oh, they've already made these selections, because guess what? After this first male was selected, they were placed back into the population. The next male was selected, they were placed back into the population. All 3 of these females, they're still in the population that's being randomly selected from. So the probability of selecting a male is constant across all selections from the population. So you would literally just say, okay, I'm going to ignore this bit of information because they're already back in my population and stick with 11 out of 38, 0.289. So I hope that example shows you how a random sample is important and how if you see the word random sample, assume that replacement is part of it. So now I'm going to talk about the unit normal table. Remember, before I've been giving you hints, like we are going to stop looking at raw data. We are going to start looking at probabilities based on the mean and standard deviation for the distribution and this thing called the unit normal table. And the unit normal table relies on z-scores. So z-scores are like the bridge between raw x values and probabilities. And so I'll give you a breakdown of what's in the unit normal table, and then in the next video, I'll demonstrate how to use it. So you've probably seen a picture that looks similar to this before. So this is just a simplified version of the empirical rule. Remember, the empirical rule states that 68% of scores are within 1 standard deviation of the mean. So if 68% of scores are within 1 standard deviation of the mean, you're left with 32% of scores. So split 32 in half. Half is here, half is here. So half is above 1 standard deviation from the mean, and half is below 1 standard deviation below the mean. So if you look at this picture, notice this is all in terms of z-scores. And then just, whatever the standard deviation or the mean is. So remember, for the z-scores, you always have a z-score of 0 for the mean, and you always have a standard deviation of 1 for z-scores. Just keep in mind that depending on the distribution, you could have any mean and any standard deviation in raw score form, but then once you convert that to z-scores, the mean is 0, the standard deviation is 1. So if you look here, so 68% of scores are within one standard deviation of the mean. So, when you're looking at raw data, you can figure that out if it's in a normal distribution. You could say, okay, the mean plus the standard deviation would be the score here. The mean minus the standard deviation would be the score on the low end. So we have predictable characteristics and probabilities within the normal distribution based on z-scores and the fact that we know it's a normal distribution. So if you think about extreme scores, so as the absolute value of the z-score increases, you know that the score that that z-score represents is getting further away from the mean. So if x is further away from the mean, then see this little lines here? That means absolute value of z. So the z-score, not considering negative or positive, the absolute value of the z-score for x is larger. So what that also means, so as your x gets further away from the mean, it's getting further out into the tail end of the distribution, x has a lower frequency. So if you think about a score that's equal to the mean, in a normal distribution, that's also going to be equal to the mode, right? The mean, median, and the mode are the same. So if you have a score that's equal to the mean, as a z-score of 0, it's right in the middle. And if you trace up, go to that score and then trace up where it hits the curve, this is a really high frequency part of the distribution, right? So remember, frequencies go from low to high, bottom to top. So this is a very common score here. But as you get further out into the distribution, further away from the mean, where the absolute value of z is larger, then let's say that you calculated the z-score for some x value, and you got a z-score of 2. Well, if you go up here, that's a lower frequency part of the distribution. It's more rare than a score that was over here. And then as you get out even further, like let's say like out here all the way to like a z-score of 5, it's like you're pretty much by yourself, right? Like that's very low frequency, very rare score. So that's getting at the x is more rare if the absolute value of z is larger because x is further away from the mean. Then x has a lower frequency, it's more rare. And now getting into probability, that means that that value has a lower probability. It has a lower probability of being randomly selected from this population or from the sample if you're looking at a sample. So think about this, and then when we start looking at the unit normal table, you can be able to visualize which piece of the graph you're looking at and what you can expect to find. So here's that picture of the empirical rule once again, and I'm going to use this picture as a reference to show you what the different columns in the unit normal table tell you. So let's take a quick look at this mysterious thing called the unit normal table. You can find this in Table B1, the back of your textbook, and you'll also be provided a copy for your quizzes. So don't freak out. You're not going to have to memorize all these values. That would just be very cruel and unusual punishment that we will not subject you to. Okay, so the table, the beginning of the unit normal table gives you a nice little description of what can be found in the unit normal table. So column A, so this column here, and you'll keep seeing, this is a pretty long table. There's column A's all over the place. But column A lists the z-score values. So where is that score located on the x-axis? Column B identifies the proportion in the body, which is just the larger section of the graph of the normal distribution. Column C identifies proportion in the smaller section, which is called the tail. Get very comfortable with body versus tail, because when you're using this table, you're going to need to know which column you're looking at depending on what you've shaded in your graph. Column D identifies the proportion between the mean and any given z-score in the distribution. And it also says here, the normal distribution is symmetrical. So remember, if you draw a line down the middle at the mean, you're going to have a mirror image on either side. So there's no need for negative z-scores because you can simply look up the absolute value of the z-score of interest and find the proportion, because it's going to be the exact same proportion that you would find if you had a negative or a positive z-score. Because it's symmetrical, it's a mirror image on either side. Now it is important to keep track if you have negative or positive z-scores, because when it comes to shading your graph to figure out what you're looking for, you need to know what you're looking at. So it's very important. Also, as you'll see in the examples, you need to sometimes, instead of starting with x and then calculating z, and then shading in your graph to figure out the proportion. You'll be starting off with the proportion. You need to visualize where that score would be located in your distribution to then use z, so you'll start with a proportion, then you'll find z to then calculate x. And you need to know, if z is to the left of the mean, it's a negative z, so that when you calculate x, you end up with a value that's less than the mean. That's abstract for now. It won't be once you look at some examples. So you can see there's also nice illustrations of what is a body and what is a tail and what is a mean to z. So let's say that we were looking at a z-score of 1. This looks like about a z-score of 1. And we wanted to figure out the proportion of scores less than a z-score of 1, or the probability of getting a score with a z-score less than 1. Remember, proportion and probability, those two words can be used interchangeably. Well, if that was the case, if you were looking for the probability of obtaining a score with a z-score less than 1, you'd be looking in the body. And specifically, you would find a z-score of 1, proportion in the body, 0.8413. Now let's say you were looking for the probability of randomly selecting a score with a z-score greater than 1. Well, that would be the tail. So you would find z-score of 1, and then proportion in the tail, 0.1587. That would be the probability of randomly selecting a score with a z-score greater than 1. Well, what if you were wanting to see the probability of randomly selecting a score with a z-score less than negative 1? So like this example, so less than negative 1. Well, that would be the tail. So if you shaded that in, you would see it's the smaller portion of the graph. And remember, I said there's no negatives in the graph. So if you're looking for less than negative 1, you would still look for 1, z-score, and then proportion in the tail. Greater than negative 1 would be a body. You would just find 1, proportion in the body. Now, if you were looking for the proportion of scores that had a z-score between 0 and 1, or between the mean and a z-score of 1, you would find the z-score of 1, look for proportion between mean and z, 0.3413, and that would be the probability of randomly selecting a score between the mean and a score with a z-score of 1. So I also break this down for you in your slides. So let's go ahead and take a look. And I'm going to use the unit normal table to confirm, kind of doing what we just did, but to confirm the empirical rule. So here I give you a little note. There's no negatives. Remember, it's symmetrical distribution, mirror image on either side. And the column A, z-scores corresponding to the position along the x-axis on the distribution. So I hope that you have your unit normal table out so that you can reference it, because I already showed you where these values can be found. So I'm not going to bounce back and forth between the slide and the table, but you can see where I'm at if you're using the table. So I'm going to use that unit normal table to confirm the empirical rule. So if we're looking at, the proportion of scores in the body, for example. And so if we're looking for scores that have a z-score less than or equal to 1, so that would be like all these guys here. So when you draw that out, you can pretty quickly see that you are working with the body, right? It's the larger portion of the graph. And if you go to the unit normal table and you find in column A a z of 1, and then you look for proportion in the body, you'll see 0.8413. And in fact, if you add, so let's see, we've got this 0.68, right? So that would be all of these. You add that to this 0.16 over here, and you end up with 0.84. Which is pretty darn close to this, within rounding error. So for the point of the empirical rule is to simplify these things. So they just rounded it to the hundredths place, or the hundredths place. Okay. So now if we're looking at the other side of this, so let's say that we were saying, okay, we want to look at, let me go ahead and erase this. We're done with you for now. So if we want to look at, all right, z-scores, or x values with a z-score greater than negative 1. So we're over here now, greater than, so remember it goes from, less than is to the left, and then greater than is to the right. So greater than -1, that would be all these guys here. It's still a body. And you get the same exact answer because remember, there's no negatives in the table. So you would just say, okay, I shaded this in. I know it's a body. Let me find a z-score of 1 in column A. Then go to column B, find 0.8413 proportion in the body. Now let's look at column C, proportion in the tail. So if we're looking for the probability, remember, I'm going to use proportion and probability, interchangeably. So the probability of randomly selecting a score with a z-score greater than 1. Well, if we think about it, okay, 1 is right here. Greater than 1, I'd be shading this guy in. I'm looking at this. It is a tail. So I would know I need to go to column C, look for proportion in the tail, and I would find that the probability of randomly selecting a score with a z-score greater than 1 from a normal distribution is 0.1587 within rounding error of 0.16 that you see here. Then on the other side, the probability of randomly selecting a score with a z-score less than or equal to -1. Well, here's -1, less than is to the left. That is also a tail. Go to the same exact spot in the table, find z-score of 1 in column A, because remember, no negatives, tail, right there, 0.1587. Now keep in mind that the unit normal table, the probabilities function like a cumulative probability, essentially. So that's why anything to the left of the distribution, so less than side of the distribution, is going to be less than or equal to. Just like cumulative probabilities tell you the probability, or sorry, the percentage of scores less than or equal to a score. But then all values to the right in the distribution, so if we're looking for greater than, we're just going to use greater than. So the probability that includes the score if you're looking for less than, and then it's just above that score and beyond if you're doing greater than. That's not a hugely important concept to understand. I just wanted to show you why when you're doing less than, you've got a less than or equal to, and when you're doing greater than, it's just simply greater than. Now that column D, proportion of scores between the mean and z. So if we wanted to know the proportion of scores or the probability of randomly selecting a score with a z-score between 0 and 1, we would be looking right here. And so you would find a z-score of 1 in the table. You're not going to look for a z-score of 0 because that's the z-score for the mean. So that's between 0 and 1. That would be between the mean and 1. So that's why you're looking at the proportion between the mean and a z of 1. So you'd go to column A, you'd find the z-score of 1, go over to column D, and you'd see 0.3413 there, which if you split this, you get 0.34. So that 0.3413 is within rounding error of that 0.34. That split 68% essentially. Now, if you go the other way with it, so I'm going to do a different color now because I like to color code things. All right, so now if we are looking for this guy, the proportion of scores between a z of -1 and the mean, which is always 0, or the probability of randomly selecting a score with a z-score between -1 and the mean, or between -1 and 0. Now we're highlighting here. We're still looking at between the mean and z. And guess what? We've got the same exact probability because there's no negatives in the table. You would just find a z-score of 1, look for column D, the proportion between the mean and z, and you've got it there. Now, to confirm this value here, this 0.68, you can add these two guys together. So we've got the proportion between the mean and a z-score of -1 plus the proportion between the mean and a z-score of 1. So that would capture all of this, right? You're adding those two together, and you get 0.6826, which is within rounding error of our lovely middle 68% of scores are within 1 standard deviation of the mean. So as I mentioned before, we can use the unit normal table and z-scores to figure out the probability of randomly selecting a range of scores, or to figure out the score that represents a certain percentile or that represents a certain probability. So if you start off with an x value, you use this formula here to calculate z. And you'll have the mean and the standard deviation provided for you. So you'll plug in your x value into the z formula, you'll calculate z, and then you'll go to the unit normal table to figure out the probability. If you're given a probability, then you'll go to either column B, C, or D, depending on the probability of interest. Then you'll find the probability in the appropriate column. Then you'll go over to column A to figure out what is the z-score associated with that probability. And then you'll use this formula to calculate x based on the z-score in the table, the standard deviation, and the mean. So this table is extremely useful. Without it, us statisticians would be completely lost because it's difficult to figure out how likely is a given outcome when you don't have access to the raw data. So normal distributions and z-scores are a very, very, very useful tool. So just a nice little summary about the unit normal table. It provides close estimates. So if we had every single possible z-score in that table, it would be really, really long table. Now there's programs that you can use to figure out the exact z-score, but for our purposes, when we're doing it by hand manually, that table is good enough. So again, not all possible z-scores are in the table, and it assumes a perfect normal distribution. So if you have your mean and you have your standard deviation, and you're trying to figure out the probabilities associated with a certain range of scores, but the scores aren't normally distributed, then that unit normal table is not going to be accurate. The closer that your distribution looks like a normal distribution, the more accurate estimate that unit normal table is going to be. Now, the most accurate way to figure out probabilities is always going to be having access to your raw data. But in most cases, we're lucky to even know the mean and standard deviation from the population, let alone have all the raw scores. So if it's a toss-up, if you have access to the raw data and it's like, okay, which one's more accurate? The raw data is always more accurate than the unit normal table. But the unit normal table is pretty darn accurate when you have a normal distribution. And so remember, typically we don't have all the raw data, so the unit normal table is an invaluable asset for figuring out probabilities.